Hello everybody, I'm here with a new topic which is not even part of the your textbook, but I think it's a good idea to have some knowledge of this. Specifically, the reason you need this concept is for purpose of simulation and using in particular the Simulink toolbox of Matlab. And within that Simulink, we would use what we call the state space. So we want to talk about the state space modeling of dynamic systems. So the whole idea here is that if we could model a dynamic system and put it in this so-called state space format, then the simulation becomes very easy. It could be done much easier. And you'll see, hopefully I'll do a video with Matlab within that. And you could see what I'm talking about. I will let you know. Now, for a linear dynamic system, the format of state space is in this form. We have an x dot, and x is actually called the state variable vector, state space vector. And we have a matrix A times x plus b times this so-called input vector. C, matrix C. So the one in red are matrices, and the one in black are actually vectors. Now by vector, I mean a vector only has, guys, the difference between vector and matrix is a vector has only, let me just erase this, right? A vector has only one column. So for example, x could be x1, x2, x3. But a vector, a matrix has more than one column, right? So that's the difference between a vector and matrix. All right, so let's come here and define each one of these. So x is called the state space vector, state variable vector. Y is called the output vector, right? U is called the input vector. And A is called the state matrix. B is called the input matrix. C is called the output matrix, and D is called the direct transmission matrix, which actually for us, this matrix would be always zero, almost, at least for the problems, examples that I'm going to show you. D is always zero, but you have to be careful when you try to put D in Simulink. You have to know the correct size of that matrix, otherwise you will get an error message. All right, so when we say x is the state vector, so remember vector has only one column, so it could be x1 through xn, so it could have so many members, so many elements. Okay, and that depends on what type of equations we have, what is our differential equations, how many differential equations we have. Like 2-degree freedom, we're going to have a system of differential equations with two equations. And then similarly, y could be adjusted based on what kind of output we want. So the idea is once the matrices A, B, C, and D are determined, then we would just take those and put them in, for example, Matlab. Then we can easily simulate and determine the response. Response is what? Output. So we get the output of the system. Now, of course, what I'm talking about right now probably doesn't make sense at all to you, but you have to see it within the context of a problem. So let's move to the next page, and I'll show you what I mean by these. Okay, so let's look at a very typical problem that you've seen many times. So we have here a mass spring damper system. I gave these values so we can actually have values. And f of t could be, the force here is an input. Input could be anything, could be a sine wave, so that makes it harmonic excitation as you've seen in chapter 3, guys. And that input, remember, is it's this vector, which in this case actually there's only one input, so the u is going to be a 1 by 1 a vector actually, or u. It's a 1 by 1 vector. Okay, so it has only one column. All right, let's get back here, get the differential equation. Now, to avoid confusion, guys, I'm not going to call the motion of m to be x. I'm going to call it z, so we don't mix up with the x's that we have here. Okay, so let's call it z. I mean, we can pick any variable we want. So we call the differential equation becomes mz double dot plus cz dot plus kz equal f of t. And so, sorry, I had to pause for a second. A phone call came in. Just plug in the values of m, k and c and get your equation. But now what you have to do for the purpose of what we want to do, just take all the terms except the highest derivative to the other side. So move 2z dot 4z to the other side, and that's what we did, and they became negative. All right, now you guys remember in this first page I had the first line of the state space format as x dot, and now I'm just showing you as a vector here as ax plus bu, right? So how are we going to do this? This is the way it's done. And once you figure this out, it's really simple, guys. So how many state variable we have? In other words, what would be the size of our x vector? This is always the first question that you have to ask yourself. If you have your highest derivative is second derivative, you're going to have two state variables. In other words, your x becomes x1 and x2. Okay? Now, if you have another equation, if you had system of equation and you had some other variable like w double dot, then you would have another 2. Then you have 4. You have x1, x2, x3, x4. Okay? But this is just one differential equation, and the highest derivative is, you know, second order, and therefore we get 2. All right. So we have x1 and we have x2. So x1, set it equal always to z, to this z. Then x2 becomes the derivative of this z dot, always. It's always like that. x1 equal the, you know, your displacement. x2 becomes the derivative of your displacement, which is velocity. All right. Now come over here. What do we need? We need the derivatives. What is x dot? So try to find the derivative of this. So what is the derivative of this? x1 dot. So I have it over here. Becomes z dot. But what is z dot? Z dot is x2. So you see, x1 dot becomes x2. Then x2 dot, if you take the derivative of this, that becomes what? Z double dot. What is z double dot? Z double dot is minus 2z dot. But what is z dot? I gotta remove this, guys. Z dot, remember a minute ago, z dot was, I have to stop doing this, otherwise I'm going to really mess myself up. So remember, x1 was z and x2 was z dot. Let's stick with that. All right, so I said x dot 2 is z double dot, which is equal to what? Minus 2 z dot. What is z dot? x2. Here we go. Minus 4z. What is z? x1. So minus 4x1 plus f of t. So far you got everything now in terms of x1 and x2. So now you go and you try to find your matrices A and B. So we come over here, we say, okay, the derivative x dot here, right? X dot here, x dot 1 and x dot 2 is equal to, remember now, here, this is already all set. This has to be a vector x1 and x2. We have no control over that. We defined it here. So now try to work it out. So look at these two equations. x1 dot is equal to x2. So 0x1 plus 1x2. 0x1 plus 1x2. X dot 2 equal minus 4x1, so minus 4x1, minus 2x2, plus, remember, this is a 1 by 1, right? And I'm going to talk about the size of these, by the way. This is a 1 by 1. So, the first equation, we don't have any input, so 0, right? And the second one, we have our u, our input, which is f of t, 1. Okay, so now, one thing to remember, guys, look, this is a 2 by 1 vector. These vectors, they all have to match. This is a 2 by 1. In order for this guy, for this matrix A, how do I know the size of matrix A? Remember, this must be a 2 by 2, because these two have to match, right? And the outcome is always this, 2 by 1, which is what I want. Same thing here. This is a 2 by 1. This is a 1 by 1. Again, these two match, and I get a 2 by 1. All right? All right, let's go and talk about the output vector, which is this guy. All right, here's the output. Now, output is entirely your choice. Sometimes the problem says, okay, I want the output to be z. What is z? Z, remember, is the displacement of this mass, and usually you want that. So if you want your y to be z, remember z is x1, right? Z is x1 right here. So your vector, your output vector is just a 1 by 1, just z or x1. So, but remember, this one you have no choice. X is always set from the beginning, and u is always set from the beginning. This is a 1 by 1. So look at the, again, this is a 2 by 1, so we need a 1 by 2, again, matching here, and we get a 1 by 1, and this becomes a 1 by 1. All right, so what do we want? We want x1 for our output, so 1 times x1 and 0 times x2. Direct transmission matrix is always 0, guys. Direct transmission matrix non-zero D is only when in your differential equation you have also derivative of your input, and we don't have that. So forget about D for the time being. D is always 0, and don't worry about that. Now, I just want to show you one other thing before I'm done with this video. I know that this is getting a longer than usual video, but let's just wrap it up here. What if you wanted to have output to be both displacement z and velocity of the mass, z prime? Then what do? Then what happens to your output? Okay, so your output now, you want to be two output. One to be what? Z, and one to be what? Z dot. And remember, z is x1 and z dot is x2. So this will give me, as y1 would be give me the displacement of the mass, and y2 will give me the velocity of the mass, right? So now look again. This is now a 2 by 1. This is a 2 by 1. This is a 1 by 1. So this must be a 2 by 2 then, right? And these dimension of these, by the way, are very important. Otherwise, if you put the wrong dimensions, the wrong size of the matrix into Simulink, you're going to see error message. This is a 2 by 1, which will give me a 2 by 1 again. So everything works out. So now, we said y1, we want to be what? x1. So 1 and 0 x2. See that? And we want y2 to be what? y2 to be x2, which is velocity. So we don't want any x1, so 0 and 1 x2. Okay, this video became a little bit longer. What I will do, I'll come back and show you a problem where we have a 2 degree of freedom system, a little bit more involved, and hopefully you will get a better understanding of that. And what I also will do is to eventually do maybe a recording on Panapto or even Zoom, sharing my screen on Matlab and show you how we can simulate these. By the way, I let go of the simulation because of lack of time and lack of logistic. So you're going to be graded only on 3, simulations. Okay, as always, thank you for watching and listening.